So, warmly welcome to today's webinar organized by the project Mistra SafeChem. It's a great pleasure to have you on board. Today's webinar is entitled Challenges and Opportunities for Green and Sustainable Chemistry. So my name is Patrik Andersson. I'm an innovation coordinator at the Swedish Environmental Research Institute. I'm also program director of Mistra SafeChem and a professor in environmental chemistry at Umeå University. Today we have four speakers that will present their work, their science in the field. We have Professor Christian Slottweg from University of Amsterdam, Professor Belén Martin Matute from Stockholm University, and PhD Tim Åström from Stockholm University, and finally Audrey Morris, professor at McGill University in Canada. A very brief introduction to Mistra SafeChem, the project Mistra SafeChem. So we have an ambition and a vision to enable and promote expansion of a safe and sustainable green chemical industry. This is a project that is in its second phase. We have been granted two steps, phase 1 and phase 2, and this second phase is up and running until 2028. So it's a research program that is targeting developing tools, methods for green chemistry with really a holistic approach. So we work with synthesis, we work with materials, we work with risk assessment and life cycle management in this project. So IVL is leading it, but we have a large number of partners that I will just shortly introduce. So if you're interested in following us, you have the web and the homepage there, mistrasafechem.se. So we have several research partners, including IVL, also the Danish Technical University in Copenhagen, Denmark, KTH in Stockholm, RISE, the Research Institute, Stockholm University, and Uppsala University. Together with the research partners, we have a group of industry partners, including AstraZeneca, BASF, Cambrex, Enginzyme, Lignicor, Merck, Nouryon, Perstorp, and Stockholm Vatten and Avfall. It's a great pleasure to have both the research side there and also the industry partners covering large companies and smaller startup companies. I will be extremely brief here on the research that we are doing. The research is starting up with working with organic chemistry, catalysis. We work also with materials. We work both with metal catalysis, but also with biocatalysis. So forming a new chemistry of interest in different fields, including circular solutions, but also pharma development of APIs. That is then followed and integrated with both the safety part, the looking and studying intrinsic properties of materials and molecules. We work both with computational methods, in silico methods, but also with cell-based methods to understand better the safety of the chemicals, both from a human side, but also from an environmental side. We are also looking at the sustainability of the chemistry driven by life cycle assessment based methods. And in this project, we are working and developing two methods, two approaches, the ProScale method and the use-tox method, mainly driven from IVL and from DTU, but also with collaboration from partners at RISE and at the Royal Technical University in Stockholm, KTH. So overall, we are aiming at developing new materials that and molecules that are aligned with safe and sustainable by design, SSBD. And this project have very much followed the development of that framework. To Chris. And Chris, are you able to share, or shall I share your slides?
Yeah, I am currently sharing.
Thank you so much, Chris. Perfect. You are warmly welcome. It's great to have you on board. I am happy to have Chris from Amsterdam here, and please, you're welcome to take over.
Yeah, thanks a lot, Patrick. And the introduction that you mentioned of Mistra SafeChem really echoes, what we try also to develop in Amsterdam. So my title is also highlighting change, ideally radical change that needs to be realized. And next to thanking Patrick and all the organizers, I also like to acknowledge my group. I guess the slides are moving. So, and also I like to acknowledge all the funding agencies that basically made it possible to share some of the results and to develop them in our labs in Amsterdam. So why change? For me, this is the most important message. Earth Overshoot Day 2 years ago was on August 1 on average. That's over all countries in the world. And actually this year, of the countries that we're presenting from, it's typically March and April that we've consumed already all our resources that were allocated for that year. And so this highlights any resource, fossil or renewable, we need to do better. We need to be more efficient. And why do we need to become more efficient? It's basically exemplified in this scheme. So the classic approach of doing chemistry is collecting resources, making products, using them, and then it stops. And often, at least part of it enters in the environment, creating a disbalance between research on the environmental sciences versus research on the making of molecules. So that is something that we urgently need to integrate, and SSBD is really one way of doing that. So the outcome is ultimately net zero. The current scheme, of course, is not zero. So how is this impacting chemistry on global planet Earth? I always really like to showcase this with the planetary boundaries concept, because it highlights our planet. It highlights also key waste problems. And also it's easy to connect molecules to them. And for quite a few of the large challenges, the chemistry is actually pretty simple. So redox chemistry of carbon connected to climate change, redox chemistry of nitrogen, and there is phosphate. And so these are often linked to nutrients that we need for food production. And basically all of these boundaries, they're interconnected. So actually solving one requires really a systemic view and a systemic change on the entire use case. Of course, it impacts biodiversity. I, on purpose, showcase this version of the planetary boundaries because now it has been quantified as well, and basically also here the message is that it's in the deep red. Why is that the case? These human-made compounds are often persistent. Think of PFAS, think of plastics entering the environment, and what is on top really problematic is that many of the molecules being produced and used industrially, we actually don't understand them well enough. And so we need more testing and understanding, ideally prior to use them on large scale. Is there some promise? I mean, definitely, because I want to highlight a paper by Steffi Helwig from ETH Zurich, and she really thoroughly analyzed if it would be possible to realize circular plastics, so net zero plastics in 2050? And the answer is yes, that is feasible. If we look at current technologies, different feedstocks, and so on and so forth, and if we really analyze it on CO2, so climate impact, but also biodiversity and pollution. And there the message is really, we can do this, but with the current scheme of biomass production, this goes at the expense of land use, because more land is required for biomass production. And it has increased pollution connected to ammonia emissions that are basically covered here in the scheme. So basically, we need to change many systems in order to realize a circular plastics economy. Another example that I really like is the recent paper from the Fraunhofer Institute in Würzburg in Germany. And there they highlighted basically the same message. You know, if you think of electricity storage and batteries, we can do this. There is a trend to use, you know, less and less scarce metals for this, from a nickel, manganese, cobalt battery. There is a shift to lithium iron phosphate, and this makes total sense. But the current technologies for recovery that can economically do nickel, manganese, and cobalt are now suddenly, with the cheaper elements, becoming economically unattractive. So this highlights, you know, we need to develop more and better and sustainable recycling technologies. And perhaps in the first place, we need to actually design products better, such that we actually can also recycle them far more easily than currently is being possible. And so we need to move from a linear economy to a circular. And the biggest change here is that the linear starts from resources, ends up with waste. Circular economy actually starts with products. And so the first cycle may be different, you know, using fossil resources, bio, CO2, you know, whatever. The second cycle ideally starts with product that still has value for simpler reuse, for example, and then moves on. And so product has to become renewable. So then actually we need to design products as such that that they can become more circular than at the moment. So this scheme basically was generated, developed in the classroom, because where I sent a message to the students, you know, circular economy is awesome, but how is this going to happen? So we developed in the classroom the principles of circular chemistry as a tool to enable circular economy, and it's very rewarding that actually, you know, now also a few journals pop up that offer a platform also for research in this area. Now, for today, I mean, in the lab, we focus on quite a few projects, but I would like to focus particularly on phosphorus, phosphates, in the case of recycling, and then how can we actually deal with contaminants in general to allow efficient and safe recycling. So why phosphates? Phosphorus in general shows a paradox. The paradox is too much in the environment and too little in the fossil mines. So of the essential biogenic elements, phosphorus is the only one that is becoming scarce at the moment. And this scheme actually, from mine to waste in the environment, was indicated already a number of decades before. So I would say now is the time to do something about it. So phosphorus is kind of urgent, because in the energy transition we swap energy carrier one for another, but for phosphorus there is simply no substitute, no replacement. So one option in general is to focus on recovery as step one, and then on recycling as step two. And there are many ways, but what is really important is that the recovery always should be in sync with the recycling, because otherwise it's far more difficult to close the loop. So actually, we showcased this at the music festival. We were teaching, the lowlanders in this case, that it's quite important to recover and recycle nutrients. We also showed them how to do that, and along the way we had an entire questionnaire that we also were aware of what they actually were donating to our toilets. And backstage, we were producing struvite and magnesium ammonium phosphate. And we used this really as a, let's say, worst case scenario. If it's possible here to recover phosphates in such a fashion that it becomes, that is suited for recycling, then basically we can do it everywhere. And the conclusion for our full analytic assessment was indeed such that this struvite produced here on site is suited for the next step for recycling. So that was pretty pleasing. The music festival is, of course, a, let's say, off-grid solution. Many countries have a grid where nutrients are collected and actually quite a few other waste streams. But all in all, it goes to the wastewater treatment plants. And then, let's say, disposable water is generated and a sludge remains that also contains the phosphate, but still some contaminants. And so the circular economy is really, if this is available already, this infrastructure, can we actually close the loop? And next, for the future, can we actually maybe design more efficient infrastructures that we can remove as many contaminants as possible? And so now you can use this sludge as a fertilizer, but be reminded that it's far from pure, contains PFAS and many other substances. So what is done in the Netherlands is actually that all sewage sludge is mono-incinerated, and then an ash is produced, which is basically a renewable phosphate. So recently, SUSFOS, together with SMB, has launched this picture on LinkedIn, where they highlighted that this current factory produced on sewage sludge ash will ideally be linked to what now is this drawing, where in a couple of years' time, if all goes well, also phosphate recovered here will be recycled into new phosphate products. And actually, the local urban mines can be exploited, and new, safe, in this case, phosphate products can be produced. So in the lab, we also focus on hydrogen carriers. We also focus on sustainable battery electrolytes and many other examples, just to provide solutions, ideally, that are also scalable. And so these examples actually are suited for recovery and recycling. But of course, there are many products that are not suited for that. I mean, think of a medicine that enters the sewage, enters this cocktail of molecules and materials, and there you simply do not want to recover, separate it from everything else, and then try to reuse and recycle it. And so for those molecules, ideally, the case is let's design them for their function, and next let's design them for a second function that is, I would call a non-toxic circularity that of course fits to the benign by design and SSBD principles. So for this, I'd like to stick to phosphorus again, but now in a context of flame retardants, because that is an interesting case. Because I mean, this polyurethane mattress is flammable. Now, to improve fire safety, we came up with the idea to add flame retardant materials that are toxic. And so that paradox is interesting, and I think is a good showcase to develop SSBD in more detail, and also see what the alternatives are at product level. And so in my lab, we make molecules. We're a synthetic chemist by training, but we also focus on product safety, the toxicity, ecotoxicity, climate impact, circularity, and so on and so forth. I mean, this makes the research far more complex than just a simple synthesis project, let's say, but also far more exciting and appealing because this is, I would say, how chemistry should be developed to generate the new materials for the future. So our scheme is, if we think of organophosphates, can we do better? The current process actually starts from fossil phosphate, then phosphate is converted to the elements, energy intense, waste intense, and then it's oxidized again and functionalized to these organophosphates. And we thought, can't we do this greener? Can't we do this circular? So using renewable phosphates, can't we use or develop a direct synthesis? So this is really ongoing in my lab. It's quite a challenge alone to improve this synthetic path. But next to that is the question: are these molecules actually safe? Because organophosphates are detected in the environment, which indicates that they're persistent. And even you can wonder, are these organophosphates actually better, more safe flame retardants than, for example, the polybrominated diphenyl ethers that we're trying to substitute? So obviously we want to avoid regrettable substitutions. We really would like to advance the field in guiding how to do safe chemistry. So really, as a starting point in my lab to explore how to do this, we were inspired by drug development, and we just selected one organophosphate that is detected in the environment. We simply computationally generated many alternative structures, then started doing QSAR-like predictions. We also use predictive models for biodegradability, toxicity, environmental fate, and we looked at the synthesizability. And then we selected some target structures. Of this one was really appealing. Why? Because these branch change are now linear, and it's actually known that linear substituents are easier to degrade in products. And we have this ethylene glycol moiety that we thought was interesting also because it can be produced from the bioeconomy. And so only then we went to the synthesis lab, start making those molecules and also experimentally verifying their properties. And this it turned out to be actually quite promising, because if we look at these two families, the one with the ethylene glycol moiety actually passed the vertical burning test, which is one indication for improved flame retardancy. So we were quite optimistic. And next case study, the second one in this line, is the one that is still ongoing. Because although it may seem easy, one molecule we substituted for another, we again use these ethylene glycol moieties as inspiration from the previous study. In general, we think phosphate should come from, let's say, wastewater. The hydroxy group in general increases water solubility, but also its biodegradation. And the organophosphate core we kept the same, because it's really related to flame retardancy properties. But we thought, okay, one molecule, it turned out to become a multi-PhD project, simply because we were learning a lot in terms of synthesis, in terms of experimentally verifying all the properties. But I think we're still on track. And so this alternative actually shows higher EC50 values. So if we determine that experimentally using algae and daphnia. And so that proved to be pretty promising. But we compared it with the chlorinated organophosphates, and also we compared it with the, let's say, the regular organophosphates with alkyl substituents. So we thought, okay, let's continue. Let's also study the biodegradability. And there actually also we observe the same trend. The chlorinated and the simple alkyl organophosphates are hydroxy ethylene glycol substituted phosphate is actually showing improved biodegradability. And not as good as the control benzoic acid, but still it also appeared to be promising. And currently we're looking into the degradation mechanisms, because that's actually also quite important. Also in terms of flame retardancy, I mean, typically we start with a simple TGA test, and that showed in the case of, again, the ethylene glycol substitute, the one, quite a bit of char formation. So quite a bit of the weight after the TGA experiment is remaining, indicating higher charring. That's good as a flame retardancy property. And that's actually similar degradation temperatures than the original flame retardant. So obviously we're continuing this with more advanced testing, also in the flame retardancy, making polyurethane foams, and adding the different flame retardants and see how they also perform experimentally. But this is actually the only way. So identify a hazardous compound, compound of concern, or should we substitute every single one of them, or can we actually redesign the product? And I'm not sure if you heard of this mattress. I mean, it's branded as Niaga, which is reverse for again. And this is actually inspired by the case of polyurethane mattress plus toxic flame retardants. And it only uses polyester. It even uses polyester for the glue, so it's 100% polyester, and therefore mechanically and chemically recyclable. And the properties of the material actually do not require additives like flame retardants. So for me, this is actually the ultimate case to redesign a product. There we can impact sustainability best, and then look at which materials do we need. Do we need additives, or can we change the properties of the polymer such that those additives become not needed anymore? And so for me, sustainability in general really focuses on 3 pillars. Green chemistry for the conversion of any resource to product that needs to be as efficient as possible. And second, obviously, safety, echoing the introduction by Patrick, focusing on human health, but also really importantly, environmental health. And as a third pillar, we really should be developing circularity much more at product level. And so either focus on buildings that become much more durable, focus on plastic bottles that can be reused without recycling, simply reuse, or we focus on, for example, nutrients that can be recovered and recycled easily. And the objective here is obviously coming back to Overshoot Day is resource efficiency. Okay, so all in all, this echoes quite well with the Stockholm Declaration, Chemistry for the Future, of which for our journal, Sustainability and Circularity, together with the other editors, we wrote a editorial piece just to echo the message of the Stockholm Declaration, which is again fully in line with the mission of this symposium also today. So with that, I would really like to thank you for the invitation and look forward if there are any questions that we can discuss in a bit. I'll stop sharing.
I have a couple of questions myself. And I started off thinking of that music festival. You talked about off-grid solutions, and you mentioned also more local solutions. A lot of us are connected to larger sewage plants today. What challenges do you see in implementing new solutions into those big investments society have made in so many years?
Yeah, that's a really good point. I mean, it's basically since the Industrial Revolution that we've been optimizing the linear economy, and now we need to, well, convince our current system at large to do better. I think we should start small. We can only start small, even if we have a pilot plant of 40 kilotons recycling phosphate, then still it's small. But ultimately, the circular economy is cheaper than the linear economy because we retain resources, we retain value in products, and then we simply have to start maybe with high value products first. But actually, the case of phosphate also shows that we can do it with low value products, where really the advantage is not transporting fossil phosphate from overseas, and actually using local phosphate waste that has a negative value, and keep it local and make products basically. I mean, also in the circular economy, in meetings, the talk is always about supply chains and how do we do this, and often I comment on, I mean, we need supply cycles. So a circular economy is circular, so also the supply chain should be a supply cycle. And probably the easiest is to develop recycling factories that are also production factories. In the circular economy, the recycling is the production of a new product. And with that vision, if we start producing locally, which also can have, benefits if you think of global politics going on, to produce more local, doing that more sustainably, I think that would be the ultimate goal.
We can also see, I mean, already now at this point in Sweden, for example, I don't know the situation in the Netherlands, there's a lot of on-site sewage treatment plants. I mean, 20% of the population is connected to their own or to small community. And we can also see that development in cities, that you have part of the cities in their own domain and making their own plants. Good. I have some questions. I'm more myself, but I also see now questions in the QA, and as I turn to the QA, and I just got a question from Jutta Hildebrand, who is asking, for the wastewater phosphate case, is source separation a relevant approach for this, reducing the concentration of contamination? Is that something you're working with?
Yeah, I mean that's of course the ideal case. If you have if you would double the plumbing, change the toilets, separate liquids from solids, that is of course more efficient. Infrastructure, as Patrick, you just mentioned, that is a challenge. So it can probably only be done in where new houses are being built, and actually in the Netherlands, in some cities that is being implemented. So also the festival example I showed, we together with a company also developed a simple active carbon filter system that just captures the contaminants, and then you can directly reuse the nutrients. So depending on the infrastructure at place, you can decide which circular solution is best. The sewage treatment is simply something we have available, and we're in the Netherlands lucky that everything is mono incinerated. So that is basically the biggest stream of phosphate available. But this is basically the linear economy adding a step to make it circular. Ideally, we need to come up with more efficient solutions.
Thank you. A last question in the Q&A is more turning into the last part of your talk, which was on redefining chemistry. Do you think there is a need to redefine chemistry to emphasize the necessity to serve humankind and protect the environment? So moving into more green chemistry and sustainable chemistry in a way. And what are the factors there? Please.
Yeah, so one is to mop up our current waste problems. And second is to design the future. that may take a while, but we need to start now. And this is something I find particularly fascinating. Thinking of the mattress, in TU Delft in the Netherlands, they're world leader in circular product design. But they're designers, they're no chemists. And from a chemistry perspective, we can design a molecule, we can design a material, but hardly ever we design a product. And so those fields, so let's say SSBD meets product design, that is, I think, the next challenge that also I try to develop. Obviously baby steps. But if this mattress was not redesigned from the polyurethane plus flame retardant example, but if we can do that for many, many other products, use the guidelines, including circular product design, I think then the future is bright.
Thank you so much. I think that's a key, starting small. There's, I guess, very few things that we have around us that started as a big project directly. It has evolved over time, and small innovations become important long term. Our speaker is Martin Matute from Stockholm University, also part of the Mistra SafeChem project. Great to have you on board, and now I can see your slides on screen. So please, Melanie.
Thank you, Patrick, for the introduction. It's a great pleasure to be here today to discuss a little bit our contributions primarily within the Mistra SafeChem project on the last 4 or 5 years. So in my research group, what we do is to develop new catalytic methods that enable the synthesis of organic molecules, and particularly very complex organic molecules. So if we think about pharmaceuticals, for example, these are very complex molecules with many functionalities, different heteroatoms specifically placed at specific positions. So it is therefore very important that we are able to construct these carbon-carbon bonds or carbon heteroatom bonds efficiently and selectively. And also for organic synthesis, is of course very important that we have methods to promote functional group interconversions, for example, oxidations or reductions. These are reactions that we are running all the time, and they have a lot of issues when it comes to sustainability. So within this context, my group has tried now for many years to develop new catalysts that enable to do these reactions as sustainable as possible. So catalysis supports the green chemistry principles. On the one hand, we will require less energy when we use a catalyst to go from the reactant to the products. If we design a catalyst for a specific transformation, we will be able to target a single product, the desired product, and therefore minimize the amount of byproducts. And this is very beneficial in organic synthesis. When we create byproducts, then we will always have to separate, and that involves the use of very large amounts of solvents and, of course, time and other resources. We can also design catalysts that maximize the atom economy so that all the atoms in the reactants are placed in the product. And also, through catalysis, we may be able to design synthetic routes that use safer chemicals and reagents. And last but not least, we can also design catalysts that enable the transformation of renewable feedstocks. So, for example, if we want to use as a source products derived from lignin, these are they have a very different composition to the chemicals we are used to have in the lab from fossil resources. So this requires a specific type of catalysis. And so overall, there is many benefits to the use of catalysis for organic synthesis. So despite the fact that when we use a catalyst, we need to add, we need to add another reagent to the mixture. The number of benefits is very large. So I have borrowed this slide from Magnus Johansson from AstraZeneca. And what I've learned from here is from every 100 million kilograms per year of pharmaceuticals that we produced, we create 15 billion kilograms of waste. So the pharma industry, in a way, is an industry that produces a huge amount of waste. And in a way, it has to do with the complexity of the materials that we need to synthesize. And for us, it also means that there is a lot of room for improvements in this area. Also from AstraZeneca, I received this slide. So if we look at the sustainability value chain, so we start from the raw materials and then we transform them. We manufacture, let's say, the chemicals or the pharmaceuticals. Then they are distributed, used, and then they are disposed. And if we look at how each of these steps contributes to the environmental impact categories, we can clearly see by looking at the blue colors here that the manufacture, the chemical production are the major contributors. And this is followed by the tableting and formulation. So this is, if we are able to work on this area, on the area of making these chemicals, I'm sure we can improve a lot the synthetic processes. And so in the group, as I mentioned, we develop new catalytic systems to be able to synthesize molecules in a sustainable manner. So we've worked a lot with metal catalyst, homogeneous catalysis, where we have a metal center, and this is decorated by a number of ligands. And the design of the ligands is key because it will provide the necessary electronic and also steric properties for the ligand, for the catalyst to do the chemistry that we want. We also work with very simple organocatalysts, and in some cases, actually, we have been able to replace a very complex iridium catalyst by a very simple organocatalyst. We also work with heterogeneous catalysts, and a major point here is that we are still very dependent on the use of rare metals for organic synthesis because they show very high selectivity and efficiency. And for example, palladium has been key in organic synthesis to make very efficiently a specific carbon-carbon bonds, for example, via the Suzuki-Miyaura cross-coupling. So what we have been working is to use metal organic frameworks and to take advantage of their porous nature to host these metal nanoparticles. And not only this will enable us to recycle the metal when the reaction is finished and reuse it, but also by carefully choosing this framework, we can also have very selective and unique reactivity. And so no matter what type of catalyst we use, we want selectivity, atom economy, safety. We want to have a very broad scope and applicability. So this case with the metal organic frameworks and palladium, this is currently one of our case studies in the Mistra SafeChem, and I'm sure we will be able to tell you about it in the very near future. So the first part of the first example I'm going to give today is on making carbon-nitrogen bonds. This is it's very important to be able to construct these bonds very selectively. If we think about 80% of the FDA-approved small drug molecules contain at least one atom of nitrogen. Therefore, making these bonds efficiently becomes very important. We can think about a very classical organic transformation to make carbon-nitrogen bonds, where we take a primary amine and we alkylate it with an organic halide, for example, a chloride, and this efficiently makes a carbon-nitrogen bond. It seems quite simple, but in reality it's very complex because the product reacts again with the starting material, forms a second carbon-nitrogen bond, and so on. So quite easily, we will end up with a mixture of products that we need to separate and purify to obtain the one we want. Not only that, in each of these steps, we create one equivalent of an acid that needs to be neutralized. So we also produce a very large amount of stoichiometric salts as waste, and we need to take care of it, of course. Of course, there are many other methods to make carbon-nitrogen bonds. We could also think about an reductive amination process, but it also requires a stoichiometric amount of reductants. So the approach that we took to make these carbon-nitrogen bonds is shown here. So we wanted to replace the organic halide by an alcohol. First of all, alcohols are safer to use. Halides, organic halides, they have a much broader toxicity spectrum, and they are also allergens. So alcohols can also come from bioresources. So they are easier to handle, and they are more available, and they are also cheaper. However, they are not good alkylating reagents. So these two reagents wouldn't react unless we have a catalyst. But another advantage of this method is that the byproduct now is not going to be a salt, it's going to be water. So overall, if we can design a catalyst that also selectively stops at the product that we want to produce, this will be very beneficial. So there are many examples of catalysts that can do this chemistry, and iridium catalysis has been very good. From the very first examples, they use very high temperatures with very low selectivity. And now the systems work much better, but they still suffer from general challenges which are quite common to all of them. They require high to very high temperatures. They require the use of bases. They usually require an excess of one of the reagents. Normally it is the alcohol. And then they also show problems with selectivity. And also they show a very limited scope. So in this area, what we did was to design, after many investigations about what was the slowest step, the rate limiting step, etc., of the reaction, we designed this iridium complex. And this N-heterocyclid carbene, which is like a bidentate ligand, is key to give to the metal the specific electronic and steric properties that are needed for efficient carbon-nitrogen bond formation. We have also this nitrogen here, and it's key because this makes this complex what we call bifunctional, and it is acting as a base as well as a catalyst, so we don't need to add a base. Importantly also, it works very efficiently, so no excess of any of the reagents is needed. And it gives complete selectivity, giving only the product that it is desired. And the yields are essentially quantitative. So this is the price we have to pay, and is to use a catalyst, but the reactions are extremely efficient towards the product that we want to form. And I will not go in detail into all these molecules, but I just want you to see that it works really well. For example, for anilines with benzylic alcohols, but we can also vary a lot the substrates, and it works with benzylic amines or with aliphatic amines, and also with aliphatic alcohols. And in all cases, it is extremely efficient, and essentially it is quantitative. This is what we really want to design. When we design a catalyst, this is the outcome that we are looking for. But we wanted to use it for more complex molecules. And so we focus on the synthesis of non-natural amino acids, because these are very important building blocks for the synthesis of pharmaceuticals. This is one example, cyclosporine, which is used for the treatment of inflammatory conditions. They can also be used for protein engineering, artificial proteins, for synthesis of biodegradable polymers, hydrogels, surfactants, etc. So it looks quite simple. Just take an amino acid. This can be a natural amino acid, and then you just introduce an R group here. So it looks simple on paper. It's just to make one nitrogen carbon bond. However, one also has to think that these molecules are quite difficult to handle, because they have an acidic site here and a basic site here, so they exist as a zwitterionic species. So they behave essentially like salts, which is therefore very difficult to purify if you have if you form different amounts of byproducts or if you have a remaining starting material left. So if we look at traditional organic synthesis without catalysis to make a single carbon-nitrogen bond, what usually we need to do is we need to protect the acidic site. So this is one reaction. Then we purify this. We make the carbon-nitrogen bond, and this may happen with different selectivity and different yields. This has to be isolated, and then we deprotect this protecting group, we take it away, and then we have the product that needs to be purified. So just to make one carbon-nitrogen bond, these are all the steps that we need to do. And for each of these steps, we need to have a reaction setup with reagents, solvents, different atmospheres, different heating, quenching, extractions, drying, filtrations, concentration, purification. So it is, we require to use a huge amount of resources and particularly solvents. So with our catalyst, we were very happy to see that actually if you take the amino acid as it is and use an alcohol as the alkylating reagent, we form the carbon-nitrogen bond in quantitative yields for all the cases that we tested. And then this is so pure, it crashes out in the reaction, so you just filter off and you have your pure compound. The solvent can be recycled and reused several times, and the catalyst can also be recycled for a number of times. And this is a very rare phenomenon for homogeneous catalysis. So this is just some of the scope so that you can see we can tolerate many different functionalities that are present in many pharmaceuticals, particularly different heterocycles. And we can put these very long chains so we can make biodegradable surfactants, and we can even apply this chemistry for the modification of small peptides. So thinking about the same, what type of chemistry, organic synthesis we can improve to minimize the number of synthetic steps, we thought about carbohydrates, because the chemistry of carbohydrate is really dominated by protection and deprotection steps. And these are usually complex because there are many hydroxy groups in these molecules. And it is important because amino sugars are part of play essential roles in biological processes, and there are many antibiotics based on the amino sugars existing today. So it's important for developing new antibiotics families. So with our catalyst, we were once again able to form selectively the carbon-nitrogen bond, avoiding any protection or the protection steps of all these functionalities here. So this is just to show that it works very well. And again, we can also place these very long aliphatic chains that with the polar head here, which is formed by the carbohydrate, then this gives access also to a family of biodegradable surfactants. So from here, we thought we wanted to look again at how nature is able to do organic or synthesis so efficiently. So usually in nature, we have the starting materials and we want to form the products, and this requires a number of steps. And what nature does is that after a first reaction with a specific catalyst, it forms the product number one, and this immediately goes to another set of catalyst to be converted into the next product, and this happens again and again until the final product is formed. So all these catalysts, they work in concerto, and they have to work at specific rates so that these intermediates are not accumulated, and then this could be a problem, for example, if one of these intermediates is a non-stable molecule. But another advantage of this, what we call nowadays tandem catalysis, is that we don't need to isolate, purify each of these intermediates, because as soon as it is produced, it's consumed. As soon as it is produced, it's consumed. So based on this, we decided to try to synthesize or design different catalysts that would be able to catalyze tandem reactions. So maybe a simple catalyst, a unique catalyst with different functions, or that several catalysts can work in concerto in the same way as nature does. So this is what we did, and this we did in the context of using carbon dioxide as a renewable building block in organic synthesis. We have a lot of carbon dioxide, so why not to use it for organic synthesis? So from carbon dioxide, we can introduce functional groups such as the carboxylic acid or the amides. We can have alcohols. We can use them to make cyclid carbonates. And these are the building blocks, for example, for the synthesis of polymeric materials. So the possibilities are very broad. But carbon dioxide is a rather stable molecule, which is good for us actually. But if we use an external activator, we will be able to react it. And this has to be by the use of a catalyst or photochemistry or electrochemistry or also biomimetic approaches. So we took the first approach in this project, which was to design a catalyst, and we focused on the synthesis of these cyclic carbonates. So these materials, cyclic carbonates, they are used as aprotic polar solvents, also raw materials for organic synthesis. And as I mentioned, they are the building blocks for the synthesis of polymers, and also they've been used as electrolytes. And so how they are synthesized is from an epoxide, which is this three-member ring with one oxygen here. So you need the catalyst and you need the CO2. So this is a cycloaddition reaction. So when we think where does the epoxide come from, they come from a double bond, which has been oxidized. So ideally, instead of oxidizing and then doing a cycloaddition reaction, we would prefer to start from the alkene directly to the cyclid carbonate. This would enable us also to not to deal with epoxides, because these are also they involve also some safety requirements, as they are very good alkylating reagents, or they are genotoxic. So what we did was to use a metal organic framework catalyst that was functionalized with a manganese ligand, and this was for two reasons. The manganese was very good for enable the oxidation, and the porous nature of the catalyst also was very good to trap the gas carbon dioxide, and this also accelerates the reaction. And not only that, when you usually do reactions under carbon dioxide atmospheres, their solubility in organic solvents is very low. So we require to use very high pressures of CO2, which means also we have to use a large excess of the CO2. So the MOF was key as a catalyst, but also to give this microenvironment that would enable the catalysis under very mild conditions. So indeed, this chemistry worked really well, and we were able to transform alkenes directly to these cyclid carbonates. And we also showed that we can have selectivity, which could be explained by the confined environment of these porous materials. But we were very happy to see that in comparison with other methods, as I just mentioned, we could use very mild conditions, and particularly only 1 bar of CO2. But then we thought, okay, what can we use exactly the amount of CO2 that we need to use? So in this way that we would not use any CO2 excess. And this we managed to do as well. And also in this case, we use chiral epoxides, because that would also give access to chiral carbonates. And in this way, these are important building blocks for the pharma industry. So we showed this as a concept that it works with carbon 12 and carbon 13, and it works very well. And this gives access to the synthesis of isotopically labeled organic compounds. And these are very important in the pharma industry, for example, to establish the safety profile of drugs via mass balance studies. But if we want to use carbon 14, then definitely we don't want to use an excess of carbon 13 radio-labeled carbon dioxide. So this method, therefore, was very good for this, and we applied this together with AstraZeneca. where they help us to produce the specific amount of radio-labeled carbon dioxide and do the cycloaddition reaction to form radio-labeled carbonates. So by being able to use a minimal amount of the radio-labeled carbon dioxide, then we don't have to deal with management of the radio-labeled waste. So in that case, this chemistry was very efficient. So within the Mistra SafeChem, I just want to mention one slide because I have discussed this project in a previous presentation in similar forum. We have also developed methods for reduction of functional groups where we wanted to replace the usually used palladium catalyst and hydrogen gas as the reductant by a nickel catalyst and water as the reductant. And we did that using electrochemistry. And the beauty of this project was that we could develop it with a lot of people also in Mistra SafeChem that assisted us to develop the method from a life cycle and toxicological assessment perspective. So from the beginning, we knew what to use and what not to use, and therefore we think we provided already a method that may be very good in the future. So if you want to read more about this project, we recently published it in Green Chemistry. So I just want to thank the students that are the ones that did all the work and the collaborators. I'm extremely thankful through Mistra SafeChem to have collaborations with the other work packages from where we are learning a lot, and also support from the industries that are involved in our projects here. And I want to thank you for your attention.
Thank you so much, Belén, for a great talk. Hardcore chemistry, organic chemistry, to more the applied side on how we take on board safe and sustainable by design in the product, where we both use LCA methods and in silico methods to, as you mentioned, design good start or have a good starting point for the synthesis, right? But also looking at the end products. I will now hand over to Tim Åström. Tim Åström is a true Mistra SafeChem scientist with the PhD from the program. He was on board in phase 1. He has now defended his thesis, and he now continues in the project in the second phase. And it's great to have you here, Tim.
So thanks for the opportunity once again to present on this Mistra webinar. Patrick already said that I work at Stockholm University, as you can see there in the background, these characteristic buildings for Stockholm University. And I did my PhD here as well, defended it last year, 4th of June, actually. And the thesis was in analytical chemistry. And the focus was to develop analytical methods to detect textile impurities, impure chemicals in textiles, both in garments but also in aqueous effluents, that I will also focus on in this presentation. So right now I'm doing a postdoc, and we are doing many simultaneous projects. A lot about recycling and upcycling of textiles, but we are also having collaborations with many different work packages within Mistra, where we are working on sustainable synthesis and catalysis, for example, in close relation to Belén as one of the collaborators. So next slide. The textile background, just to give you a little brief introduction. For long I have been saying that textiles may be considered as a forgotten source of daily human exposure to hazardous chemicals in clothing. But one question might be, how well known is the chemical content in clothes? And can we really say that it's a forgotten source? Because people are becoming more and more aware of their health risks, and that clothes actually are could be harmful from a human health perspective. And then you can click there. Yes, there are various different classes in textiles, chemical classes that may pose significant threats to the human health. Some of them might be cancerogenic, mutagenic, cause skin sensitization effects, something that we are particularly interested in our group, to study the allergenic properties of different chemicals. But these are typical chemicals that have been detected by previous researchers in the past. So considering this, then we can say that textiles are not a forgotten source. It's well known that chemicals exist in textiles, and this is really what I want to point out. Next slide, please. And you can click here so that we get everything. I just briefly want to mention here that there are regulations within both European Union and the US. For example, we have REACH that you are well aware of, that covers many different substances. We have the SVHC, substances of very high concern, which covers almost 250 different compounds. We have the prioritized list, and we have the restricted substances. Although there are very few chemicals that are regulated or restricted in REACH. So that's sort of a limitation, that the regulations needs to be updated and improved consistently, because we need to regulate more chemicals, and therefore we also need the analytical methods to prove that chemicals are there. Otherwise, we don't know what to regulate. Similar to the REACH, in the US they have the Toxic Substances Control Act that covers more than 86,000 registered substances. So far more compared to REACH, that covers more than 26,000 compounds. So there are regulations, regulatory acts, but they are quite limited. That's what I want to point out here. Next slide. And then you can bring up here all the animations. This is just to show you how the chemicals are introduced to the fabric, because the textile chain is very complex and there are many different steps where chemicals can be introduced to the fabric. And first of all, there are 3 different kinds of chemicals. We have functional chemicals, process chemicals, and unwanted chemicals that we don't want, but they still end up in the garments. And we are particularly interested in those chemicals that we don't want to be there, the byproducts. These are chemicals that we have good methods to analyze. But functional chemicals, they should be in the garments for a specific purpose. For example, water repellency or dyes. Process chemicals can be, for example, detergents, because the garment is washed before it's delivered to the retailers multiple times. So there are various kinds of chemicals. Fast fashion is another problem, because chemicals are frequently being changed, or new chemicals are introduced into the garments because of new demands on the market. And that's really a problem with fast fashion, that chemicals are being rapidly introduced into the fibers. And that also highlights the importance of developing new analytical methods so that we can detect new chemicals, and not only look at those chemicals that are regulated under the street lamp, so to say. We want to detect new chemicals so that we do something novel, right? Approximately 25% of chemicals that have been detected in textiles, they are associated with at least one adverse health effect. And according to Swedish Environmental Agency, approximately 3,500 chemicals are associated to the textile production. This number is a little bit ambiguous, so of course there might be much more today. Next slide. There are environmental impacts and health consequences, as I said. Cotton, for example, is associated with a very high consumption of water. And the textile industry also pollutes the wastewater, as various large amounts of dyes are released into the effluents up in production. So that's also a huge environmental problem. And also the dye precursors and the byproducts are also released into the effluents, which is another problem, because when textiles are dyed, the dyes that are being used, they are not typically 100% pure. This is something that we have seen in my research, or in our research, that the dyes are not 100% pure, and they may often contain these dye precursor molecules, which is not a good thing, because if they are there as free compounds, they could also migrate to the skin and cause allergenic effects. They will be released up in laundry, for example. We have a very nice paper that was published recently, just a couple of days ago, that is all about laundry of garments. So you can check out on that, because we did a comprehensive study where we investigated cotton and polyester, and we could see clear differences by looking at these two materials, in fact. So that was a very nice study that was published recently. Yes, you can continue there with the yes, and also, as I said, skin sensitization is a quite large problem, and that is something that we are interested in our group, because we want to study textile allergy. And it's considered that approximately 1% of the Western population suffers from textile allergy. 1% doesn't sound like a big number, but if you consider the whole Western population, we are talking about millions of people that might be affected, right? 1%. And that's only. Then there are other health effects, such as genotoxicity and endocrine disruption. For example, phthalates, they are considered strong endocrine disruptors, and they are also frequently found in textiles today. Next slide. So, what are my responsibilities within phase 2 of Mistra? We can continue there, pick up the animations. Well, as a big part of my thesis, we developed the thermodesorption GCMS method, which is a very fast method and straightforward. We only need about 10 to 20 milligrams of textiles, which is significantly less compared to conventional techniques where we use solvent extraction and offline GCMS. And this technique offers less minimized sample preparation and not as much lab consumables as we need when we do solvent extraction. That is also a plus, because we want to be environmental friendly. It's challenging to say that the technique is sustainable, because many things are associated with sustainability, but we can at least say that the technique is greener, because we don't have to use any solvents, hazardous solvents, like dichloromethane, for example. But one should be a little bit cautious when talking about sustainability, even though it's a nice word. Yes. The method is also quite fast. We can analyze chemicals in less than 40 minutes of acquisition time. So it's significantly faster compared to other methods, and is suitable for a wide range of volatile and semi-volatile compounds. Next animation there. Yes, and I also want to say that the technique or the method was proposed to be a new national standard or a new European standard by European SEN. So it's currently being evaluated to become a new standard in SEN and also in SIS, Swedish Institute for Standards. Next slide. Just to show you how does it work. I mean, the technique is straightforward. We do a primary desorption of the textile for 10 minutes at 175 degrees. And during this desorption, all the volatiles and semi-volatiles are being concentrated on a T-nex cold trap. That's the first desorption. Very straightforward. And then if we continue a little bit with the animation, we have the secondary desorption where we desorb the cold trap. And all the chemicals that are trapped on this cold trap, they are transferred to the GCMS for analytical separation and detection. And this process is fully automatic, which means that you can load up to 50 samples in the tray, leave it, and the instrument takes care of the extraction and the acquisition. So that's basically what we have been developing here at Stockholm University. Next slide. I just want to show you a typical black polyester sample. And as you can see, there are many different compounds in there in the chromatogram. Of course, we can look at many compounds that we have standards for, but there are many other peaks that we also are interested to identify. And this we can do with non-target analytical workflows, where we try to annotate all these peaks that are in the chromatogram. But this is just to show you the complexity of a typical textile sample made of 100% polyester. Next slide. And of course, it's important when you develop methods to show that they give the same result as the conventional methods. So we have, of course, validated the ATD technique towards solvent extraction and offline GCMS. And in both cases, we got a one-to-one linear relationship for these two analytical platforms, suggesting that we can quantify accurately the polyester samples, synthetic polyester samples. This is also true for cotton samples that we have a paper on. Cotton is a little bit more complicated because of the possible hydrogen bonding that you might have with the fiber. But it works. It works very well, and we get the same results as the conventional method. And currently we are working within Mistra SafeChem phase 2. We are working on premium textiles, where we are trying to prove the same concept for fibers like wool, silk, viscose, and so on. So more premium textiles that are a little bit more expensive, or other materials that we haven't looked at before. Next slide. Yes, we continue there. My time is running away a little bit. We're having a collaboration with organic chemistry, where my part is to identify byproducts in the crude mixture, in the crude product. And this is just a typical reaction that they made using metal organic frameworks, the Nobel Prize of 2025. And as you can see here, the byproducts that we were detecting with GCMS, they were very low because we quantified them very efficiently. And as you can see, all of them are less than 0.5% or 0.1%, which is a good thing because we don't want impurities. So this is one of the projects that I'm enrolled in. A very nice sustainable catalysis using metal organic frameworks. Next slide. And then in another case study that I'm also enrolled in, we are looking into the upcycling of worn out textile apparel, where we want to use it for a better purpose instead of incinerate or subject the clothes to landfills, which is not very good for the environment. So we want to achieve a sustainable recycling of clothes, basically. Next slide. And then we have a process where we do tempo oxidation. So basically, the tempo reagent attacks the C6 carbon in the cellulose chain. Cotton is made of cellulose. And the hydroxyl group is replaced by a carboxylate group. That's the tempo oxidation to make the cellulose more bulky. So you can go to next slide. And then in step 2, we can do the fibrillization using a microfluidizer in order to create the cellulose nanofibers. And depending on the number of passes that you do, you can get a better yield. So in this process, we have a total yield of 66.4% for the CNF, the tempo oxidized CNF. So in terms of yield, it's acceptable. And of course, my part is to see, if you go to next slide, that is to see what impurities that are formed, or if we have any transformation products in this process. And that you can do by non-target analysis using LCMS, high resolution mass spectrometry, where you study the starting material, the cellulose nanofibers, and the aqueous waste. So that is my part, to do a more comprehensive non-target screening with LCMS. So then if we continue to next slide. So this is basically a comparison that I have been doing for the starting material and the CNF, cellulose nanofibers. So features that are more to the left in the plot, they are more significant in the starting material, while those features that are to the right, they are more significant in the CNF, not in the nanofibers. So we can see that we are able to achieve a much more purified product compared to the starting material. That is a good thing. We don't want chemicals to be transferred to the product. So if you go to the next slide, then one can ask, what happens with all these chemicals that were found in the starting material? Well, then we also analyze the aqueous effluent, because that is important. What was released in the effluent. And here we can see that far more chemicals are more significant in the effluent. So then we can start to think a little bit, and maybe this is because of the oxidation, that chemicals are oxidized into something else. So therefore it's important to try to assess the toxicity of these transformation products. That is important. Although we are, if you go to the next slide, if we are looking at the distribution of substances, then we can also see that legacy chemicals are removed to a very high extent. So like phthalates, for example, we were only able to detect 2 phthalates and 1 phosphate, but these were removed to a very large extent. And these are also regulated by EU. So that is a good thing. The same was also true if you go to the next slide. If we look at library matched substances in the process, library matched means that they are not confirmed with a reference standard, but they are still likely to be there because they are matched with a library. There is still some sort of uncertainty, of course, but we can see that the majority of these chemicals are removed or degraded into something else in the process. And this is really what we want to show, that maybe the chemicals is efficient enough to degrade chemicals. Yes, and if you go to the next slide, then we can see that some chemicals, they are actually generated in the process, suggesting that tempo oxidation can generate oxidized chemicals into something else. And then we see a significant increase in the effluent, as we can see here for some chemicals. And this is an interesting thing. So of course here we need to do a proper toxicological assessment in order to understand if these chemicals can pose a threat to the environment. And of course then one should also consider the possible dilution that we might have in wastewater. That is important. So next slide. So the next step in the process, this is probably my last slide. We want to do tempo oxidation of polyester and cotton and acrylic cotton as blended fabrics. That is very important because currently we only did it for 100% cotton. That is one thing. And if you continue, then as I said, we want to do toxicity prioritization, for example, by calculating margin of safety values in order to easier evaluate the environmental exposure for specific compounds that we have been able to detect. And that is what we will focus on in the coming months within phase 2. So I think that's everything from me. Thank you.
Thank you so much, Tim. And with that, I would like to welcome Audrey to the stage, and we're so happy to have you on board all the way from Canada, and to give you a presentation on recent developments in your group. So please, Audrey, stage is yours.
Thank you so much, Patrick. Can you hear me well?
We can hear you very well and see your slide.
Thank you so much. So it's really a delight to be ending this really great lineup of speakers today. I'm really delighted to be here on Earth Day, amongst other days. So this is really great. And yeah, you made me reflect on this question. What are the challenges and opportunities for green and sustainable chemistry? And I think that there are many, and I will today reflect a little bit on some of the work we've been doing, trying to carry home the notion that mechanochemistry can be a great way to achieving that. So I'll show you a little bit of that today. Just before we start, we're at McGill here in Canada. We're located in the Montreal area here, about a few hours north of New York. It's still very cold here. We had snow even this week. I also want to acknowledge the fact that we are situated on land that used to be a site of exchange for Indigenous people, Haudenosaunee and Anishinaabe in particular. So I want to keep this thought in mind today. My group has been really developing research on 3 different pillars, really. This idea that we want to take biomass as our resource, and I will explain a little bit more what it means. We're also developing new synthetic method that we hope to be greener, and in particular, mechanochemistry plays a key role here, and I will develop that as well. And we are also working in the notion of metrics and assessments. You will see today that a number of things that we're doing are measured. I will not spend too much time on this, but obviously this is something that Mistra SafeChem is doing really effectively, and I really look forward to working more with you guys on these types of aspects. I think there's a lot that we can develop. I will highlight here some papers that we have in that space. This is really developing a lot of frameworks to understanding the toxicity of nanomaterials. So I won't talk too much about this, but if you have questions, I'll be happy to answer. So really, challenges and opportunities for green chemistry and sustainability. I really tried to explain a little bit some of the ways that I'm seeing things. A lot of these ideas have been introduced by prior speakers, especially Chris at the beginning made a fantastic introduction to these topics. And in particular, it discussed circularity. I think one of the things that we do in chemistry is focusing a lot on the process itself, because this is what we know best. This is what we've been educated in. But the reality is that we need to really consider the entire system in order to truly develop green chemistry. In other words, developing here a process that is green is not sufficient. You also need to care about what's coming before. and where it is going. And again, we've seen some fantastic examples today of people thinking this way. So resources is really important, and resources is the way that we can actually move forward. And in the context of global warming, climate change, we know that what we want to do is reduce emissions of carbon. And one of the mechanisms that has been proposed to do in that is to transition from an oil refinery, which is currently the dominating way that we're making all the materials and the energy that we use, towards a biorefinery in which we take biomass as our resource. And as you can see from this very schematic slide, you have what you have to do when you do that is change the process so that you can make materials, and sometimes materials that differ from the ones that you made from fossil resources, because you are starting from a different resource. But the benefit would be that CO2 could be sequestered in that cycle, enabling to lower the greenhouse gases emissions. So this is really what people are trying to see as being a beneficial mechanism towards reduction of greenhouse gas emissions. So the target has been developed by a number of people, but biomass is really seen as one key player in its ability to replace fossil-based economies towards a more virtuous economy that would be potentially carbon neutral. So in order to illustrate that, I'll take you through a quick journey on one example of what this looked like in the context of biofuels. And one example is biodiesel. The diesel engine was invented more than a century ago by Rudolf Diesel. And what is really interesting about this is that Rudolf Diesel, when he invented this, actually started to make the diesel engine work with biomass-based fuels. So in fact, when he actually presented this invention to the French government for an exhibition, he actually used the arachide oil, so peanut oil, as a demo for that. And it's only later when people realized that the diesel fraction of oil refining was not useful, that they realized that they could use it with this engine, and it became the diesel that we know today. But the problem is that biodiesel, so people now are trying to go back to the roots and trying to reintroduce biodiesel as a possibility, and it has been done. And one of the key players in that sense is Indonesia. So in Indonesia, we consider that half of the palm oil industry is geared towards the production of biofuel. So what is happening in this country is that the primary forest has been cut down in order to grow palm trees, and half of it is used for human consumption or animal consumption, but the rest is used for biodiesel. And this has caused a number of consequences, in particular to biodiversity. Indonesia is one of the top mega biodiversity countries, and in particular, populations of monkeys have been affected by that. And what we know is that, so this is from actual serious research, people have demonstrated and validated that key parts of the forest in this Indonesian island have been affected, and thereby reducing the effective land that was occupied by these 17 primates in the land of Sumatra. So what this means is that, yes, I mean, we need to be carbon neutral, and it's really essential to reduce our emissions, but as Chris introduced earlier today, we need to also have a wider view onto this problem and integrate the planetary boundaries in a larger extent. So climate change is definitely a part of that question. No discussion around this, but we have to also take into account these other aspects, including the biosphere integrity, which I just discussed in the example of the Indonesian monkeys. So what we need to do is to develop a framework in which, instead of only looking and measuring carbon emission, we go beyond and we consider all of the planetary boundaries. And I'm just showcasing here an example from the group of Gil and Gonçalves in ETR, showcasing how they've been able to introduce this in the specific example of the methanol economy. So if I go back to my original statement that I want to use biomass, I want to develop a biorefinery, I need to be particularly attentive now to all of these non-climate planetary boundaries, and I want to be particularly attentive to 4 of them: the biosphere integrity, land system change, freshwater use, and geochemical flows, because these are the ones that are actually primarily affected by the use of biomass. In other terms, we really need to integrate more biomass. There's no question about this. But when we do that, we really need to also think, are we going to affect monkeys in Indonesia? Are we going to transfer land that would be used for agriculture to now the use for growing chemicals or fuels? Are we going to have an imbalance in PNN geochemical flows, as Chris discussed at length? So this is really with that lens that we've approached our own research and trying to develop what would be a circular economy. In that context, we're thinking, a great source of carbon, one that is wasted in really large amount, is actually food waste. So it's considered that about 1/3 of the food waste that is produced globally is actually wasted. And it is a great source of biomass, because otherwise, what are we doing with it? We are usually downcycling it. Ideally, we compost it, which is actually good, but in most cases, it's just landfilled and not even really valorized. So what we want to do is to do that, but of course, it comes with a number of challenges, right? Because biomass is not... biomass waste is a really complex mixture of things, and we need to develop chemistry specifically to that effect. What is difficult here to tackle, and really the challenges that I wanna put forth here. I mean, again, Chris discussed really in amazing ways this notion of introducing circular chemistry. But we have to also be mindful of the great economic challenge that come with that. When we are developing a circular economy, we have to deal with more complex mixtures than what the chemical industry is usually accustomed to, especially coming from oil resources. There's been a great effort in refinery, we are separating things and we are making pure streams that what we do when we deal with these biomass mixtures. So this notion of complexity is one of the challenges of circularity. Another challenge is the fact that when you are digging for oil and you are recovering oil, you're not paying for the fact that carbon storage took place here. Whereas when you're starting from biomass, you have to make an effort and actually do the transformations all the way to equivalent molecules. And that cost is borne by the people who are doing the circular economy. So I think that this is really saying that there are these challenges, and one of the ways that you can overcome this is, on the one end, really reducing the cost of separation and deconstruction, so developing better processes for that. And then also on the other side, trying to find uses that are going to really bring value to the materials that you make, so that you can overcome the fact that you are not paying for carbon storage when you use fossil resources. So again, I'll try to show you some examples of that, of how we develop that. So if we think about this notion of using biomass waste as a resource, we can turn to something called the blue bioeconomy. So it's this idea of using marine resources as a mechanism to extract some valuable molecules. So what you can see on this slide here is that crustacean waste, for instance, is a great resource for these 4 different chemicals. Chitin, chitosan, which I'll be mostly talking about today, because this is the material that is present in sufficient volume in crustacean waste while actually bringing economic value. But there's also proteins there, minerals, as well as pigments such as astaxanthin, which have high value but now are present in small quantities. The paradox in this industry is that we generate a really large amount of this waste globally. So for instance, between 6 and 8 million tons of waste from crabs, shrimps, and lobster are produced yearly on the globe. In Quebec, so this is the map of my own province in Canada, Quebec, we produce 40,000 tons of this same waste. And right now in Quebec, we're not using it at all. So the best we could do with it is to do a form of composting. But obviously there is an opportunity to do much more because chitosan, so one of the molecules I said is present in these materials. This is, so crustacean waste is the #1 source of chitosan out there. This is a really big and dynamic bioeconomy market where we have applications that span from nutraceutics, biomedical, fertilizers, fibers, as well as water treatment. Water treatment is particularly interesting because people are really trying to replace petro-based chemicals by chitosan right now for doing especially trapping of heavy metals in water. So there's a great potential, but at the same time, how come we're not making use of all of that? There's really something that is paradoxical here. And the paradox comes from the fact that the way to extract these molecules is really not ideal. So essentially what you have to do, so if you take here a crustacean shell model, you can see that it contains chitin, proteins, and minerals. What you have to do is do 3 steps. So first demineralization, deproteinization, all of that in a slurry with large amounts of acids and bases. And finally, from the chitin, you need to do a deacetylation reaction. So really using chemistry here to turn my amide group here into an amine group. This is how you unlock the potential for all of these applications. But the problem is that this, all of this chemistry requires the use of corrosive and viscous liquids, such as highly concentrated caustic soda solutions. You need to heat, you need to manipulate those chemicals, which is actually dangerous for workers. But the biggest problem, the one that actually made some of those plants shut down, is the fact that it generates a lot of aqueous effluents. So essentially, all of this process requires a lot of water, and then a lot of water for cleanup, separation. And all of that water doesn't contain anything really toxic, but nonetheless, the load in salts is too high. And just the cost of handling that is too much. And most companies in the Western world have just stopped working in that space. So there's really a need to develop a better processing for that. So in my group, we're interested in mechanochemistry. This is the way that we're doing chemistry using mechanical energy. This allows us to work in the solid phase. So when we do that, you could use here more pestle or mechanized version like vibrational mills. We also use aging, which is something in which we let reaction happens without the mechanical action after we have mechanically activated the materials, which allows us to modulate the chemistry and have a more selective and effective chemistry going on. And some of the things that we found this type of chemistry is very useful for is when you work with recalcitrant substrates, so substrates that don't dissolve into anything, such as crustacean shell waste. When you need to reduce solvent use, here we have this question too, because we want to reduce the quantity of water we use. And finally, when we're trying to do some new chemistries, and I will show you some example of that in a moment. So what we developed is a process by which we could take crustacean shell waste, turn it into chitin, so extracting the chitin present in there using solid acids, such as malic acid or citric acid. We demonstrated that when we do that, we really reduce drastically the footprint of the processes, whether this is in terms of mass or in terms of energy. We've also been able then to take chitin and through mechanochemistry and aging, which plays a key role here, I'll be happy to answer questions on that if you have some. We are able to now turn it into chitosan with reduced quantities of waters and chemicals to an extent that it now becomes feasible from an economic standpoint to develop them as a process. We're also reducing the energy use as well as the safety for operators as we do that. And we have patented these processes, and we're now working on scale-ups with a tech transfer company. And we're really excited to work now on these processes at the scale of 10 kg, using partnering here with folks that are on the north coast of Quebec, fishermen there, who are generating these large amounts of waste on a yearly basis just for the crab industry. So we have a lot of stuff that we could do with that. And we're working with tech transfer companies, CDBQ here, where we have access to some of the large-scale processing facilities, such as here, this food processor that is allowing us to work under multi-kg scale. And what is really interesting here is that we're really working hard now on through this notion of how do we deal with the complexity of the starting materials, and we really look forward to developing continuing developing this into a pallet scale that we hope we can install up north in Quebec within the next year or two. But in the lab, we wanted to sort of push that, and we have developed a number of different processes based on these types of ideas. So now we have access to chitin, now we have access to chitosan. What can we do with that using mechanochemistry so that we can offer a wider range of products? Because as I mentioned earlier, what's also key is not just to take the resource, but also to develop new products that are going to have high-end applications so that we could really valorize them to the extent of what we need. So we've developed a mechanochemical and aging-based process for the tuning of the chitosan molecular weight, which allows us to do this with great precision. We've developed as well some functionalization tools so that we can now add different functionalities onto chitosan with unprecedented degree of substitutions. And we have managed in particular to do that for the introduction of tertiary amines onto chitosan to make really highly charged, positively charged amines, which have a lot of applications that we're trying to develop now. And we've validated actually that we could do that on other polysaccharides, such as chitin itself for starting material, but also from cellulose. And in particular, what we can do with that is start with wood pulp and directly treat wood pulp with this chemistry so that we can make charged cellulose into this one-pot process. And what is really cool is that once we've done that, we can actually, with a simple ultrasonication of 5 minutes, have access to nanofibers. The same nanofibers that was just presented earlier by Tim when he was showcasing how the Andrews group was making nanofibers from cellulose from cotton clothes. So what we can validate here is that if we take wood pulp and we introduce our chemicals there, we can, with a low energy defibrillation, access readily these really very well defined cellulose nanofibers. You could see they're very high quality, they're very thin, and they have a length of about 1 micron. And this is really interesting because these materials have really high-end applications. So you will recognize here the tempo oxidation that Tim was talking about earlier. And these materials usually require the use of a high-energy defibrillator. And you saw that as well in the example that was that was discussed for the clothing valorization project. So this is cool because these types of materials can have a number of applications, including here their use in as pent ink, as demonstrated by the group of Akira Isogai in Japan. Another thing that we've been doing is trying to see if we can take advantage of some really nice feature of biomass, which is that it has an intrinsic structure. So we can take chitin here and extract chitin nanocrystals. And so this has been known, but we've developed a process by which we can do that by mechanochemistry. And then another thing that you could do is take the nanochitin and turn them into nanochitosan. So these nano whiskers of chitosan, which we're now learning have a lot of really great applications, for instance, for making gels or for wound healing. And I'll just give you a quick snapshot of this last example of how these nanochitosan can be highly effective for wound healing. So the idea here is that what you're trying to do is to develop what's called a nano glue. So this concept that you could take some nanocrystals, nanomaterials, and use them in as a surgical glue to try to help with healing, in particular in the context of surgery. So an example of what this could look like is you take here my hand, I have a cut, I want to put a band-aid. This is just an example so that you understand what we're doing, but a more realistic one would be in a surgery context. But let's say we take your hand, you take the band-aid, and what we do is we put, before we put the band-aid, we put the nano glue, here in this case, a nano whiskers of chitosan. We could then apply some sonication so that we help with penetration. Then we add the band-aid on the surface of it, and then we try to remove the band-aid. And as we do that, we are actually measuring how much energy we need to apply in order to remove the band-aid. And when we do that, we realize that under some conditions, we could get very high adhesion energy, meaning the band-aid is really well stuck on the hand. We've done some electron microscopy in order to understand what's going on there, and we validated that when we are putting with this setting, we're able to construct this sort of foam material in between the skin on the right and the band-aid on the left. You could see more of its structure here. And all of that is composed of the nanochitosan that is forming this kind of scaffolding, holding together the skin and the hydrogel very effectively. This positions this material here in a much better position than other materials that have been used before, whether polymeric or nanomaterials. And another added advantage is that if you try to remove the band-aid multiple times, you actually can't, because you have crack pinning mechanism coming in that enables the material to be extremely stable. Again, if you use it in the context of your band-aid, maybe not the most desirable thing, but what this means is that if you're using it in surgery, it really makes a glue that is highly effective, highly stable, and highly resistant to mechanical trials. So I think this is some kind of cool application that we can find from these emerging and new materials. So hopefully I've shown that you could use these types of systems, and especially mechanochemistry, to on the one hand access these high-end materials while having a very low energy and materials input, lower than the slurry-based equivalent materials. We also have demonstrated we could get really high yields, which is really nice. And we've developed applications for the hydrogel, microfibers, nanoglues, drug delivery, and so on. And we're continuing to work with people on that space. There is great need actually to develop more understanding of the safety and toxicology of this. We have good indication that it should be good, but this is work that we're trying to develop at the moment to have that understanding. I'll finish by giving another couple of snippets of the work that we do. For instance, we are making also microfibers with pure chitosan so that we can make hierarchical structures with pure chitosan, which is biocompatible and antibacterial. So we are working on these types of things for, again, biomedical application. This is some really cool projects by Ishnit. And finally, I will close here by telling you that hopefully I convinced you that circularity must be implemented, that waste should be a privileged resource. Mechanochemistry is a strategic tool with that because it's uniquely able to deal with complexity while preserving structures. And I showed you some examples of that today. And the applications must be aligned with the property of the resources. And, oh, I'm sorry, the end of my sentence is gone. And also have economic value so that we could overcome this problem of starting with the resource competing with oil. With that, I want to close and thank you again for your attention. Here is again what we're doing in the group. And I want to acknowledge the fantastic people who have done the work. I've shown a lot of work from Ishnit. This is the microfibers, the microfibers, yeah, at the end. Tony Jin, who did a lot of the work on the nano chitin, chitosan, as well as Galen doing a lot of work here on the functionalization of chitosan with mechanochemistry. I also wanted to say that I started my appointment as a guest professor, a WISE guest professor at Stockholm University, where I'm interacting with a number of you folks. So I really look forward to enhancing these collaborations and working more in particular with Mistra SafeChem. And I want to acknowledge all the fantastic people I've had the chance to work with, the funding, and I will close by wishing you all a happy Earth Day. Thank you so much for your attention.
Fantastic, Ori. Thank you so much for this very inspiring talk. And I heard the rumors about the WISE position. You are congratulations and warmly welcome to also to network even more with Swedish scientists. And of course, we hope to see you also in the in collaboration with Mistra SafeChem. Great talk. Time is running, but just a few thoughts on your talk. You're working in a very challenging area with, as you say, the complex starting materials for bio-based materials, and I see that you have there are openings and there are promise and there are things. But what about how is it now with interest, the market interest, and you ended up talking about now of course we need to compete with the fossil-based chemistry, which is the major source for the chemical industry. How can we move forward? What are your thoughts from your particular applications here? Are there needed political initiatives to get it going, or what are your thoughts?
Yeah, so I really think that this is going to take a number of pushes. So I think on the one end, we chemists need to develop better processes and better materials. So definitely there's still a challenge here. But I do worry a bit indeed that if we do not have better help as well from governments and incentives from regulations, that it will be hard to overcome all of the premium that we have to go against. So I think that one of the strategies that we've approached is trying to find some really cool applications for these materials that are going to enable us to enter the market with these kind of products, generating revenue that will allow us to then go for larger volumes in the future. Because there is here something to bear in mind. We need to have a market size that matches the resources that we have, while at the same time generate enough revenue that this is profitable so that the company can survive. So it's we really live in a little bit of that conundrum. On the question of chitosan itself, we think we are in a good position, but we're still actually working the math on what this could look like as a strategy. So this is still ongoing research and ongoing discussions in our group with the partners that we have for this project. So I don't have an absolute answer right now, but this is something that we're really attentive to, and we started to develop these thoughts around this stages approach, where we are first trying to find some cool applications, pushing in this direction while we are developing a larger volume strategy over time.
Thank you so much, and I would like to, with this, also take the opportunity to thank all speakers. We are now running to the end of this webinar. I think it's been great to listen to the variation of talks from organic chemistry to the phosphorus issue to now also talking about the bio-based, and not forget the huge issue of textiles and chemicals in textile that we are facing. It's great to be on board in the Mistra SafeChem project, where we are developing a lot of methodologies in the area of sustainable chemistry and green chemistry. Please follow us on our LinkedIn, and we also have a webpage where we regularly publish news. This webinar will as well be published there and on our LinkedIn page. With that, I thank all speakers and the audience, and those asking questions on the QA. And have a good day. Thank you so much.
All right. Thank you.